So let's map both sides by G. So I'll have G of F of A is, now G of F of A is just A, okay? And G of, no, we G both sides in a sense. So G of F of B, G of F of B is just B, right? That's true for any element, including B. So G of F of B is B, right? Now, if we G both sides, GF of A is the same as GF of B, okay? But GF of A is A, and GF of B is B. So GF here is A, and GF of B is B. So A equals B. So A equals B. And that implies F is injective. Hope you followed that. Okay? So we're going through the details of the proof. This is only like step 1 of 4. Okay. Alright, surjective. How do you prove something is surjective? What's the general strategy to prove something is surjective? This is from the previous lecture. Well, you take an arbitrary point B in your codomain. Here's your function f, right? And you have to find some element in A, big A, so that f of A equals B. And if you can do that for any B, you can find an A that maps to it. That means that every element, little b, in your big set, your codomain, big B, every element here gets mapped to, right? At least once. And by definition, that means this f is surjective. Surjective means on, so it's an onto function, or a surjective function. We want to find a mapping that, something's like this. So let's start with B. Right? We're taking an arbitrary element B. Now we know this is true. Okay? We know that's true. So now we can use this. So B equals F of G of B. Okay? So let this here, let that be your A. Right? That G of B, that is your element that maps to B. Right? That G of B. That's your element A. Okay? So if you put A in here, like if G of B is A, then f of A takes you to B. Okay? And we know that's true. F of G is B because it's given in statement Q. Here it is. F of G of B is B. Okay, so your element here that maps to B is this one, G of B. Right? And we know it exists because we're told that. Right? We know that's true. All right. So that G of B, little b, that's the element that maps to little b. So, and B's, you randomly chose that. Could have been any element in your codomain. So this is true in general, and therefore it's surjective. So therefore F is surjective. Okay, and we just true before that it's injective. So if it's injective and surjective, therefore F is bijective. Alright, so we've done half. Now we've done 2 parts of 4. Okay, so we've now done the if part. How about the only if? So P only if Q. P is true only if Q is true. The only way you can have P was if Q was true. So if you do have P, you must have had Q. So if P, then Q. So the only if, I'm running out of, I'll do it here. So the only if case, that's if P, then Q. Okay. So this time, so we're proving it from left to right now. I've done this many times now, you're probably used to this. Alright, so we start now with the assumption, we're assuming that F is bijective is true. Okay? Now, so we're assuming F is bijective. Now if it's bijective, it's 1-to-1. Okay? And that makes things very easy if it's 1-to-1, because if that's your A, it maps to B. So, and it's 1-to-1. So your B must be of this form, F of A. Right? Now it's 1-to-1, so if you've got a function going the other way, G, that means that G of B will take you back to A. It must, right? It must, because it's 1-to-1. Okay? There's no other way. So if your G's going that way, F going this way, so your G, and because it's 1-to-1, your G of B takes you back to A, okay? But B is F of A. So G of F of A equals A. And that is here. Okay? Now we can do something very similar. So we've now done like 3/4 of it. Now we do something. Let's start now with B and G it, and we'll go to A. Now it's 1-to-1. We can do this. That's 1-to-1, right? So G of B. So you're applying to little b here a function going that way from right to left, from codomain to domain in a manner of speaking. Although with respect to function G, it's the other way around. You know, this now is your domain, and that becomes your codomain when you go that way. All right. So if you G this little b here, you apply the function G to this little b, you'll get A. Okay. So you've got that. Okay. But again, it's 1-to-1. So if I F my A, I'll get B. Right? So F of A gives me B. Okay? It's 1-to-1, so I can do that. But A here is G of B. So F of G of B equals B. Right? FGB is B. FGB is B. And that's it. We've proved theorem 30. Okay. Now I'll need to clean the board. Alright. But before I do, I'll just make a statement. I can now label this G, this function G that takes you back along a bijective path, if you like, in a sense. You know, if this G is cancelling out what F does, you know, with these properties, so it's taking you back to where you started with. So in a sense, it's like the inverse function. Well, it is the inverse function, okay, and that's what it's called. So we now label that G the inverse function. Now I think, let's see, so theorem 31, I think you're proving it's, that it's unique. Oh, now theorem 31 will do two things, but I'll do that after I clean the board. Theorem 31 says that this G here, this inverse function, has two properties. It's bijective and it is unique. So we can talk about the inverse function to F. So this G is the one and only one inverse function. It's unique. So I'll clean the board and it'll be theorem 31, and then you can see the next topic when you have three functions like f, g, and h. That those three functions, so you'll have like four sets, you know, four ovals, Venn diagrams, if you like, and we'll prove that when you have three functions, composite, so f, g, and h get used to make a function with three components, f, g, and h. We'll show that that f, g, and h is associative, right? So I'll stop there for a moment.